We'd like to take a look at an example where we will be finding the volume of a solid with known cross-sections. Let R be the region in quadrant 1 bounded by the graphs of y is equal to 1/4 x squared, which is a parabola, y is equal to 4, which is a horizontal line, and x is equal to 0, which is a vertical line. It is the y-axis. So region R is the region bounded by, first of all, it's in quadrant 1. Region R is in quadrant 1. This is quadrant 1, above the x-axis and to the right of the y-axis. R is the region in quadrant 1 bounded by these three graphs. So this is our region. So now that we've identified region R, let's continue reading the problem. For each y between 0 and 4, so y starts at 0 and y ends at 4, from y is equal to 0 to y is equal to 4, cross-sections, the cross-section of the solid perpendicular to the y-axis is a rectangle whose height is twice the length of its base in region R. So what that means is we're going to make a three-dimensional solid using this two-dimensional region R as the bottom or the base of our solid, and we're going to build up from this base up towards the sky. And this particular part that I highlighted from the problem statement tells us that when you take a cross-section of this solid perpendicular to the y-axis, each cross-section will be a rectangle whose height is twice the length of its base in region R. So what does that mean? Let's see if we can try to visualize the solid. Suppose we take a cross-section perpendicular to the y-axis at y is equal to 1. So we'd be looking at this red line segment on the base of our solid. And we're going to build up from this red line segment so that our cross-section perpendicular to the y-axis will be a rectangle whose height will be twice the length of the base. So for this particular segment, the length of the base will be 2 units. So twice 2 would be 4. But if you were to draw a horizontal line segment at y is equal to 4, which is at the extreme edge of our base, the length of that horizontal line segment is 4. So twice that would be 8. So where you draw the rectangle where you are looking at the solid will determine the height of the cross-sectional rectangle, because depending on where you are looking, you can have the horizontal line segment at the base be longer or shorter, and since the height of the rectangle depends on the length of the base, we need to have a function of y that will give us the area of each cross-section. And why do we need a function of y that will give us the area of each cross-section? Because as we learned, the integration formula for finding the volume of this type of solid is the definite integral from c to d of the integrand is a function of y that would give you the area of each cross-sectional surface. And why do we integrate with respect to y in this example? Because we're taking cross-sections perpendicular to the y-axis. So everything has to be in terms of y. The integrand giving us the area of each cross-sectional surface must be a function of y. The limits of integration must be y values. We can begin to write our definite integral by recognizing what the limits of integration should be. We're starting at the very bottom of this region at y is equal to 0 and going to the very top of this region at y is equal to 4. So the limits of integration will be from 0 to 4. We are integrating with respect to y. So all we need is our integrand, which must be a function of y, and it needs to tell us the area of each cross-sectional surface, which we know from our problem statement will be a rectangle whose height will be twice the length of its base in the region. So we really need to find a function of y that will tell us the length of the base in region R. And as we discussed earlier, that depends on where we are looking in the solid. So how do you find the length of this horizontal line segment? You need to subtract the x-coordinates of the right and the left endpoints. And we want to write the x-coordinate as a function of y. So how do we do that for a point on the parabola whose equation is y is equal to 1/4 x squared? We need to solve this equation for x. So we multiply both sides of the equation by 4 and get 4y is equal to x squared. And then we will take the positive square root of both sides of the equation. And the reason why we take the positive square root is because we're looking at quadrant 1, where x coordinates are positive. So we have x is equal to the positive square root of 4 times y, which you can write as the positive square root of 4 times the positive square root of y. The square root of 4 is 2. So we have 2 times the square root of y. So that is x in terms of y. So for example, you can test this out. When y is equal to 1, which is the segment that we're looking at, we know that the x-coordinate of this point should be 2. Well, if you substitute 1 for y here, the square root of 1 is 1, 2 times 1 is 2. And when y is equal to 4, if you're looking at this particular horizontal line segment, we should get that the x-coordinate is also 4. And do we get that? Substitute 4 for y here. The square root of 4 is 2, and 2 times 2 is 4 for the x-coordinate. So that is, in fact, how we can assign coordinates to the right endpoint of an arbitrary horizontal line segment in region R. And for the left endpoint of this arbitrary horizontal line segment in region R, we can assign coordinates as follows. Y is variable between 0 and 4. X must be 0 because for the left endpoint, it's always on the vertical line, x is equal to 0. So now the length of this horizontal line segment is given by the difference of the two x coordinates, right minus left. So we will have 2 times the square root of y minus 0, and that will be, of course, the base of our rectangular cross-section. But what we need for the integrand is the area of each cross-sectional surface. So how do we get that? Well, knowing this is a start, but now we have to go back to the problem statement, which states that each cross-section perpendicular to the y-axis is a rectangle whose height is twice the length of its base in region R. What that means is the height of the cross-sectional surface depends on which cross-sectional surface you're looking at. It is also a function of y, but we know that it will be, in fact, twice as much as whatever the base is. So we know the base is given by this function of y, which we can simplify to just 2 times the square root of y. When you subtract 0, it doesn't really change anything. So we have 2 times the square root of y for the base. And we know that the height will be twice that, which means it'll be 4 times the square root of y. And how do you find the area of a rectangle? Well, you multiply length times width, or in this case, base times height. So when you simplify, this is what you get. Volume is equal to the definite integral from 0 to 4. 4 times 2 is 8. And then you have square root of y times square root of y, which is y. And you can factor out the constant factor of 8 if you'd like. But this is our definite integral. It's from 0 to 4 for the limits of integration. So 8 times the definite integral from 0 to 4 of y with respect to y. And that will give us, the value of this definite integral will give us the volume of this solid. But since the instructions are write but do not evaluate a definite integral that gives the volume of the solid, we may stop here.